Okay, solve the initial value problem. 2y prime plus 4 is equal to y squared plus 4x with the initial condition y of 0 is equal to 9. And you can see the steps are kind of laid out here. We want to use substitution. We're going to let u to be some expression. Then we're going to convert this differential equation into a differential equation in terms of u and u prime. Hopefully, with the correct substitution, it will be linear, right? Because notice this one is nonlinear because it has the y squared term, which makes it much more difficult to solve. Then we're going to solve this new differential equation in terms of u, solve for u, using the techniques that we learned, integrating factor or variation of the parameter, whatever method you like. And then we're going to, again, use this expression, plug it in, back in for y, and find the general solution in terms of y. And then we're going to use the initial value to find the particular solution for y. Okay, so first things first, we have to figure out what substitution we want. Now, notice first off that the problematic term, so to speak, is this y squared, right? It's the nonlinear part. And notice that on the left-hand side, we also have the derivative of y squared, right? This is y squared, derivative of that with respect to x, right? Our derivatives are with respect to x. And because this is by the power rule, it's 2y, but also since y is a function of x, we have to multiply it by y prime by the chain rule. And so this is going to give us the intuition for our substitution, right? If we let u be y squared, then the derivative of u with respect to x, u prime, again, on the right-hand side, the derivative of y squared with respect to x is 2y times, again, y prime by the chain rule. And now you can see we can plug this back in to our equation. On the left-hand side, we get y prime plus 4 is equal to y squared, or u, plus 4x. And now you can see this equation here is completely in terms of u and x. It has no y's left over. As a side note, this question asks for y is equal to something and y prime is equal to something. Whereas here I've written u is equal to something and u prime is equal to something, which I find is simpler for this question. But we can rearrange this to find y and y prime. So what we do, from the first equation, we get y is equal to the square root of u. And then if we differentiate both sides of this new equation with respect to x, on the left-hand side we get y prime. On the right-hand side, by the power rule, we get 1 over 2 square root of u. But also by the chain rule, we have to multiply this by u prime. And so these two expressions are the expressions you would put here and here. Okay, but that's more just to answer the question. To actually solve this new equation here, I'm going to write it in the linear standard form. Right, if I move u to the left-hand side and then move that 4 to the right-hand side, right, this is the same form as y prime plus p of x, y is equal to q of x that you probably are familiar with. And again, we can use an integrating factor or variation of the parameter or whatever method you were taught. I'm going to use an integrating factor here. And so my integrating factor is going to be e to the integral of the coefficient on u, which in this case is -1. So it's just e to the integral of negative dx, which is e to the negative x. And so I'm going to multiply both sides of this equation by e to the negative x. So on the left-hand side, I get e to the negative x u prime minus e to the negative x u. And on the right-hand side, I get 4x minus 4 times e to the negative x. And so on the left-hand side, right, the reason we do this is we're going to get our integrating factor, e to the negative x, times u, the derivative of that. And I'm just going to copy down the right-hand side. All I did here was rewrote the left-hand side in terms of a derivative. And so now we want to solve for u here. And so we got to kind of unpack. You can see u is kind of buried inside the derivative. And so we got to take the integral of both sides with respect to x. So here's what I get, 4x. On the left-hand side, right, the integral of a derivative just gives me the inside part, e to the negative x times u. On the right-hand side, you can see we have a product of two functions. I'm going to first, before I determine this, I'm going to factor out the 4 from the first part here. And we have to try to find this integral of x minus 1 times e to the negative x. Now you're going to have to, again, because it's the product of two functions, the method we have to use here is integration by parts. So I'll kind of copy this down here and do this integral quickly. This video is not meant to be sort of a tutorial on integration by parts, so I'll go through kind of quickly. We let u to be x minus 1, so the derivative of u is dx. The dv becomes the other part times dx, and so v is negative e to the negative x. And so now this integral becomes u times v, so negative x minus 1 e to the negative x, minus plus becomes a plus e to the negative x dx. And so if I put that minus sign through in the first part and then do the second integral, I get negative e to the negative x. And because we need an arbitrary constant, right? Because eventually we're going to be plugging this integral back into this for this. And so our general solution is going to need an arbitrary constant. And notice that we have negative x plus 1 of e to the negative x, also minus 1. So we can sort of factor out the e to the negative x. And the plus 1 and the minus 1 will cancel, and we'll just get negative x of e to the negative x plus our arbitrary constant. Okay. So that is that integral. And so I'm going to plug it back into this equation. So I get e to the negative x times u is 4 times our big expression here, e to the negative x plus a constant. And on the right-hand side, we get negative 4x e to the negative x. And we get 4 times our constant c, which I'm just going to combine into one constant. So I'll write c sub 1 for all of this, and I'll just combine this into a new c, which is 4 times the old c, right? A multiple of an arbitrary constant is still an arbitrary constant. That's equal to the left-hand side. And I want to solve for u, so I get u, multiply both sides by e to the positive x. I get negative 4, and then the e to the negative x will cancel again to be 1, plus c e to the x. So this is the solution for u in terms of x for that differential equation that we had back up here, right, this one. But we want the solution to the original differential equation in terms of y. So I'm going to plug back in u is equal to y squared, negative 4x plus c e to the x. And this is a solution, right? It's not an explicit solution because I haven't solved for y just yet. And if I do solve for y, I'm going to get y is equal to plus or minus the square root of negative 4x plus c e to the x. Now the plus or minus comes into play is if y is positive or y is negative, right? If I have a plus sign, then y will always be positive, right? Because the square root is always positive, or not, or I should say non-negative. Right? It could be 0 or positive. And if I put that negative sign in front, then again, the square root will always be positive. So the negative times the square root will always be negative, or I should say non-positive. So in other words, y will always be less than or equal to 0. And so that's going to depend on our initial condition, right? Our initial condition was y of 0 is equal to 9. And so if you plug that in, well, I'll just plug it in to this equation because it's a little bit simpler. So I get 9 squared is equal to negative 4 times 0 plus c times e to the 0. So 9 squared is equal to c, or c is equal to 81. And again, notice that when I plugged in 0, I got a positive y value. So this means that we're using the positive version of the square root. And so our particular solution is negative 4x plus 81 e to the x. And so this is our final answer for this initial value problem.